All right, guys, we're moving on to equilibrium, and I had you watch those other 3 videos. Hopefully you watched them before you are watching me go over these notes with you. I would be strongly recommended that you start writing some of this stuff down in your notebook, since it looks like we're going to be out for at least another 2 weeks, and I want to make sure that everybody understands what equilibrium is. So if we have, let's say, a reaction, I'm going to write one up here. You can see that the reaction goes in this forward direction. That's why I have an arrow pointing to the right. But the arrow can also point to the left. And if it points to the left, it means it's going in the reverse direction. And if you have a reaction that's going both in the forward and reverse direction, what that means is that the hydrogen and the oxygen are becoming water at the same rate that the water is turning back into hydrogen and oxygen. Okay, so this is the important thing to remember on this slide. Equilibrium means the rate of the forward, that means going from left to right, is equal to the rate of the reverse, which means from right to left. Okay, so you have to remember, when you have equilibrium, let's get a pen again. This is the important part. Rate is equal rate. That's the speed. So the speed going forward and the speed going reverse is equal. The other thing you have to remember is that concentration is constant. Whoops, let's write concentration is constant. Concentration is constant. That means when you look at the reaction, it doesn't look like anything's happening. But in fact, it is. And there are 3 different types of dynamic, meaning changing equilibriums, that we have listed here on this page. The first one is phase equilibrium. That's like saying you have H2O solid becoming H2O liquid. That's melting. At the same time, the liquid is becoming a solid. This is phase equilibrium. It's occurring in a closed system. So what that means is if you have let's say you have a bottle of soda, this is a bottle of soda, and you have carbon dioxide gas here, and it's becoming bubbles up here. Hopefully you can see this because it's awfully small. The CO2 liquid is becoming CO2 gas at the same time the gas has become liquid, and it only happens when that cap is on the bottle. So that's phase equilibrium. Then you have solution equilibria. Okay, solution equilibria happens when the reaction is saturated, and by saturated you remember that all the seats are filled. So if these are all the seats that we have in our stadium, remember we talked about the seats, okay, and I fill every single one of those seats with a particle, any extra particle you put in is going to fall to the bottom. That's how you know it's saturated. Well, if one of these guys comes out of his seat, then the guy who's on the bottom is going to go back into his seat. It's not going to look like anything's changing, but in fact it is. So the rate that it is dissolving, going from a solid into the aqueous solution, is equal to the rate of the undissolved settling out. And then finally we have chemical equilibrium. That's like this guy up here where a chemical reaction is taking place. You can look at sodium and chlorine becoming sodium chloride. Not balanced. That equation is not balanced. We could balance it. We could put a 2 here and a 2 here. If the 2 sodiums and the 1 chlorine become 2 sodium chlorides at the same rate that the sodium chloride is becoming sodium and chlorine, then it is chemical equilibrium, because there is a chemical reaction taking place here. Okay, so that's equilibrium in a nutshell. What you have to remember are these 2 things. Equilibrium, rate is equal, concentration is constant. I'm going to show you a quick little graph on the next slide. Okay, so this graph should look familiar to you because it's what we did in the lab last week. And I'm going to do my reactants. I'll do my reactants in blue and my product in red, just so you can see. So if my reactants are blue, doesn't matter what those reactants are, they will become my product being red, okay? At the beginning of time, you'll see that I have the word concentration here. At the beginning of time, I have 100% reactants. And at the beginning of time, I have 0% products being the red one. As time goes by, so time marches on here, 1 minute, 2 minute, 3 minute, 4 minute, 5 minute, the amount of reactants that I have is going to come down. And the amount of products that I have is going to come up. Eventually, these guys are going to level off. Okay? And the concentration is going to become constant. It's not going to change. So right about here, it levels off. I know that's a black marker, but you get the idea. Okay? And they are parallel to each other. When they are parallel to each other, we can say that the reaction has reached equilibrium. Okay? So that kind of relates to the lab that we did last week. And I just wanted to point that out to you. All right, now, getting back to kind of what we talked about last week with collision theory, Le Chatelier's principle. Let's get a highlighter here so you can see what I'm looking at. Oh, that's gray. Cool. Le Chatelier's principle says we can now change and manipulate that equilibrium so that it is what we want to happen. And we're going to do that by making more collisions, right? And we can make more collisions by changing the concentration, we can change the temperature, we can change the pressure, we can add a catalyst. We can shift the equilibrium so we get more reactants or more products depending on what we do. And again, this relates to the lab that we did last week when we did collision theory, okay? If I want to, let's say I have a reaction, I'll just take this reaction now, H2 plus O2 yields H2O, and it's at equilibrium. That means the hydrogen and the oxygen, the hydrogen and the oxygen are turning into water at the same time that water is turning into hydrogen and oxygen. The rate is equal. But let's say I want to make more water. I want to make more of this. I need it to go faster to the right than to the left. What do we need to do to make that happen? Well, we need to get these hydrogens and these oxygens to collide more frequently. We need them to hit more so that they become water faster than the water is turning back into hydrogens and oxygens. And we can do that by changing the concentration. We can do that by changing the temperature. We can do that by changing the pressure if there are gases involved, and we'll just make these gases because hydrogen's a gas and oxygen's a gas. We can also add a catalyst, and when we add a catalyst, we'll make the hydrogen and oxygen collide more frequently. All right, so if I get the hydrogen and oxygen, if I put more hydrogen in here, let's say we have a box, and these guys are my hydrogens, and these guys are my oxygens. They're going to collide with each other. But if I start adding more hydrogens, the black ones are my hydrogens. If I start adding more, now they're going to collide more frequently. And more collisions between the hydrogen and oxygen will shift the equilibrium to the right. It'll make it go faster to the right. That's called a shift in equilibrium. Okay, now how are you going to figure out how this works? Anytime I increase the concentration of anything in a reaction, hold on, let me erase something. Okay, I erased it. Let's say I add more hydrogen. You see how the hydrogen is on the reactant side? If I add hydrogen, my reaction will shift to the side that is opposite what we added. So we added hydrogen, I'm shifting to the right. I'm going to make more water formed. Because hydrogen is on the reactant side, we say it shifts to the right. If I added more oxygen is still on the reactant side, it will cause the reaction to shift to the right as well. It's going to cause more collisions between the hydrogen and the oxygen, and therefore you're going to be making more of whatever's on the opposite side. What happens if I add more water. If I add water, now the water is going to collide with other water molecules because that's the only thing that's on that side, and the reaction is going to shift to the left. So what I want you to remember is anytime you add something to the reaction, no matter what side it's on, you shift to the side opposite what you are adding. All right, the next one is temperature. So I'll grab myself a red pen right here. Let's look at temperature. Temperature works exactly the same way. If we add temperature to this reaction, let's say temperature, sometimes it's written as heat, sometimes it's written as a number like 575 kilojoules, okay? That's what you're adding. If I add heat or temperature or kilojoules, whatever, to the product side, it is an exothermic reaction. Exothermic means heat is being given off. It is exiting. If heat is exiting and I add heat to it, it is going to force my reaction to go to the side opposite of what you're adding, just like concentration did, but now we're going to force it to the reactant side. If, however, you had a reaction that was endothermic, let's say I have lithium and chlorine and heat, and it made lithium chloride, and it's endothermic now. Endothermic because I'm putting heat in. If I put heat in, heat is going to force the reaction to go to the right because heat is on the left, so the reaction shifts to the side opposite what you are adding. Shift to the opposite side of the energy term. Okay? Let's get another page here. Okay, the last one that we're going to look at is pressure. And pressure only affects gases. So this is how it works. If you have gases, and these are both gases, how many gases do you have here? You have 2. So you have 2 moles, 2 groups of a gas. And here you have 1 mole of a gas. That means you have a total of 3 moles of a gas on the reactant side. Here on this side, we don't have any gases. See, it's a liquid. Okay, so it's 0 moles of a gas. So 0 moles of a gas. Anytime you are dealing with pressure and you want to know which way the equilibrium is going to shift if you affect pressure, what you're going to do is you're going to shift to the side with the less number of moles. This guy has 0 moles, this guy has 3 moles, so I'm going to shift to the right because I shift towards the side with less moles of gas. You have to only count gas moles, not liquids or solids or aqueous, because the only thing pressure affects is gas. So add them up, add the gases up, and see which side has less, and you'll see which way it shifts. Now this is called the Chatlayer's principle. Which way is my equilibrium going to go if I change the concentration, change the temperature, or change the pressure? Okay? Catalysts are a little bit different because a catalyst speeds up the reaction in both directions at the same time. It doesn't segregate. It doesn't say, okay, I'm only going to deal with the reactants or I'm only going to deal with the products. It makes the reaction speed up in both directions. So it starts speeding up this way, but it also speeds up this way. And therefore, there's no shift in the equilibrium when you have a catalyst. All right, I know this video got a little bit long and I'm sorry about that, but I don't think that you could do this without me trying to explain it. So hopefully you get it.